Okay, so we are now ready to start the last module of this course. And this is the module on digital electronics. And if you want to read more about this, the place to go is Eggleston, chapter 8. Not all of it, but a substantial part. Malvino doesn't discuss digital electronics, but in general, also if you look online, there'll be lots of resources, or if you find some other book, please feel free to follow that. So, first question, of course, is what is digital electronics? So far, everything that we have been doing has been analog, meaning it's like a continuous signal. If you consider a sine voltage, which has amplitude of, let's say, 10 volts, then this voltage can take all possible values starting from 0 to 10, 0, 0 0.1, 0 0.2, all the way up to 10, even intermediate values. It's a continuous variable. It can take all possible real values between 0 and 10. Now, this, of course, has some disadvantages. The main one being that for any kind of signal, for any kind of circuit to work, you might be interested in a specific value of the signal. So for example, let's say you want something to be triggered at 5.6 volts. Then it has to be exactly 5.6. You don't want it to be 5.5 or 5.7 or anything else. But your signals are never pure. You might have some sort of AC voltage generator which claims to give you a sinusoidal wave, but it will never be, what you get in your circuit will never be exactly sinusoidal. There will be some noise in the circuit. There could be some stray electromagnetic signals that your components will catch. There could be some ripple. We studied how when you're converting from AC to DC or from DC to AC, you often get some sort of unwanted ripple in your circuit. So you can get all of these kinds of effects which make your measurement process difficult. And when you say you want exactly 5.6 volts, you may not exactly get that. So that's the main problem with analog. So to beat that problem, we go to using digital values. Digital is where you have only two states, a low state and a high state. So a two-state system. An analog signal in principle has infinitely many states, as many as there are real numbers. But when you are working with digital electronics, you are only concerned with two possible values. You can call these 0 and 1. So that's all you're concerned with, nothing intermediate. So instead of 0, because of noise, because of stray signals, because of ripples, for whatever reason, instead of 0, if you get 0.1, 0.2, that's okay. You will still consider it 0. Instead of 1, if you get something a little bit more or a little bit less than 1, that's fine. You will still call it 1. But eventually, whatever calculation, whatever circuitry values that are needed for these things, you will always consider them to be either only 0 or only 1. So that's the advantage of using digital over electronics, over analog electronics, that you only have to deal with two states at a time. So the first thing that we're going to do is we're going to look at the binary number system. So first, before we do that, let's do a quick recap of the decimal number system, which is what we always use. This is in base 10. And the reason this evolved in base 10 is essentially because we have 10 fingers. And when humans first started counting, we started counting on our fingers. Therefore, base 10. So what does the decimal number system mean? So suppose I have the number 5043. and I'm going to put a little 10 as a subscript to denote that I mean this number 5043 in base 10. So I actually mean the number 5043. So what does this number mean? This number means this is 5 times 1000 plus 0 times 100 plus 4 times 10 plus 3 times 1. So that is the meaning of 5043. That's the meaning of these digits 5, 0, 4 and 3. Or I might write it as 5 times 10 to the 3, 0 times 10 to the 2, 4 times 10 to the 1, 3 times 10 to the 0. So what these coefficients are, what these digits 5, 0, 4 and 3, these numbers, these digits are just coefficients of the power of 10. So if I want to express any number in base 10, all I need to do is I need to put these coefficients together, and that is what gives me this number 5043. How many such coefficients do I need? I need 9 coefficients, which is 0, 1, 2 till 9. If I just have these 10 symbols, then I can express any number in base 10 in decimal. So in general, when I am working in base n, I need n number of digits to express a number, any number, in powers of n. So we can do the same thing. We can define the binary number system, which is base 2. So now I'm going to need 2 digits, and these 2 digits are 0 and 1. And now any number I can express in terms of these 2 digits in powers of 2. So for example, if I write the number 10110, and now I'm going to put a little 2 subscript to denote that I don't mean 10,110, I mean the number 10110 in base 2. So how should I write this? I will write this in terms of powers of 2. So 0, 1, 2, 3, 4. So this is going to be 1 times 2 to the 4 plus 0 times 2 to the 3 plus 1 times 2 to the 2 plus 1 times 2 to the 1 plus 0 times 2 to the 0. So what is this? So this is 1 to the 4 is 16, 8 is not there, 4, 2. So this is actually 22. 22 in base 10 or in decimal. So the number 22, what we call 22 in decimal, in binary it is written as this. So let's write down what all the binary numbers look like, the first few binary numbers. Let's do it in the next page. So let's say decimal, binary. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do 10 more. Let's go up to 20. So 0 is just 0, 1 is 1, just to make it easier for you to see. 2 is 1, 0, 3 is 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 1000, 1001, 1010, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. One zero one one. Oops. 1100, 1101, 1110, 1111, 10000, 10001, 10010. Don't worry how these came about. We will discuss how to calculate it just now. But I'm just listing out the numbers for you. If you have done binary before, you probably know how this happens. If you haven't done binary before, maybe you might have spotted some sort of pattern when I was writing down the numbers. But anyway, let's see exactly how we go about translating from one system to another. So we're going to look at both binary to decimal as well as decimal to binary. So first, binary to decimal conversion. This is exactly how we discussed what I said before. So if I have the number 10101, then basically you know that this is the power of 2 to the 0, which is 1. This is the power of 2. This is the coefficient of 4, coefficient of 8, coefficient of 16. So this is just 1 times 16 plus 1 times 4 plus 1 times 1. So that is 16 and 4, 20, and this is 21. So 10101 in base 10, in base 2 is 21 in base 10. I mean, you don't always have to write down like this 1 times 6, 1 times 4, and so on. You can just see which are the ones which have a 1 in them. So if you just write down the power of 2 on top, you can just see this is going to be 16 plus 4 plus 1, or 21. Let's take one more example. If I take 1010, and this is power of 1, coefficient of 1, coefficient of 2, coefficient of 4, coefficient of 8. So this number is just 8 plus 2, which is 10. You can also have binary numbers, of course. So for example, I might have 1010.0011. So what do you do after so you separate out first, before decimal part, after decimal part. So this part, before the decimal, you do the exact same thing as we did before. So we have seen 1010 is just 10. Let's take 1011. This is just 11. After the decimal, so before the decimal, we do positive powers of 2, right? We do 2 to the 0, 2 to the 1, 2 to the 2, and so on. After the decimal, you do the inverse powers of 2. So this is basically 0 times 2 to the minus 1, 0 times 2 to the minus 2, 1 times 2 to the minus 3, 1 times 2 to the minus 4. So this is going to be half, 1/4, 1/8 plus 1/16. So this is going to be 2 by 16. So this is 3 by 16. So you can calculate how much that is. So this is basically the number 11 plus 3 by 16. This entire thing. So that's how you deal with numbers which have a decimal point in them. Now let's look at the inverse question. If you have a decimal number, how do you convert that into binary? So there are a couple of ways of doing this. One is just the usual method. So suppose I tell you convert 53 into binary. So well, you can, so first we can list out the powers of 2. We can say, okay, there is 0, there is 1, 2, 4, 8, 16, 32, 64, and so on. We will not need 64 because 64 is greater than 53. So if I want to express 53 as a sum of some of these numbers, I don't need 64. Up to 32 is enough. Now let's just see what numbers do we need. So definitely I will need 32. Then how much is left? 21 is left. Then I will take 16. Now 5 is left. How do I make 5? 5 is 4 plus 1. I don't need these two. Basically, I'm trying to find out which of these numbers add up to give me 53. So 32 plus 16 plus 4 plus 1, 20, 52, 53, correct. So these give me 53 total. So wherever I put a tick, you put a 1. Wherever there's a cross, you put a 0. So 110, 101. This is the binary way of writing 53. Let's take one more example. Suppose I want to find out what is the binary representation of the number 25. So once again, let me list out all the powers of 10, powers of 2. 1, 2, 4, 8, 16, 32 onwards I don't need. So which of these numbers do I need if I want to write down 25? I will take 16. So let's put a 1 over there. 16 and 8 is 24. So let me take the 8 also. Only 1 left, so I'll take the 1 and I'll put zeros everywhere else. So 11001 is the binary way of writing 25. But there's another method which is, so this kind of method is fine as long as your number is not too large. So if I ask you to find the binary representation of 7963, then it's going to be a little annoying doing this, because then you will have to write down 1, 2, 4, 8, 16, blah, 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 512, 1024, 2048, and so on. It's doable. It's not the most efficient way of doing it. So there is another way of finding out how to do the decimal to binary conversion. And this is called the double dabble method. How does this method work? Suppose I give you some large number. Let's take the number 1. Well, this is not a very large number, but let's take it anyway. Let's take 101. No. Let's take 94. I want to find out what is the binary representation of the number 94. So what you do is, you keep dividing by 2 and you note down what is the remainder you're getting each time. So when I divide by 2, I get 47, and then the remainder I get is 0. Now again divide by 2. 47 when I divide by 2 I get 46, 23, and this time remainder is 1. Again divide by 2. 11, remainder 1. Again divide by 2. 5, remainder 1. 5 you divide by 2, I get 2, remainder 1. Again I divide by 2, I get 1, remainder 0. And finally again divide by 2, I get 0, remainder 1. So now I have taken all these remainders. What I will do is I will just put them in reverse order. So remainders in reverse gives you 1, 0, 1, 1, 110. And this is the answer. Let's verify if this is true. 1, 2, 4, 8, 16, 32, 64. Oh, you can't see very clearly, can you? So let's add up all the ones where there is a 1. So 64 plus 16 plus 8 plus 4 plus 2. How much is this? 16 and 4 is 20, 30, 94. Correct. So here's how you do it. You keep dividing by 2 successively and you collect all the remainders and put them in reverse order. This is called the double dabble method. What about cases where you have numbers after the decimal point? Okay, for that, let's take an example. So suppose I give you the number 15.875 and I ask you what is the binary representation of this number. So first of all, separate out the before decimal from the after decimal. Just first let's look at 15. So 15 divide by 2, you get 7, remainder 1. Again divide by 2, you get 3, remainder 1. Again divide by 2, you get 1, remainder 1. Then divide by 2, you get 0, remainder 1. So 15 is just 1, 1, 1, 1 in binary. Now we'll look at the part after the decimal. So we have 0.875, right? Now what we're going to do is we're going to keep multiplying by 2. So this gives you 1.750, right? Yeah. So now every time you get a 1 before the decimal, you make a note of it. And now again you multiply the rest of it by 2. So if you just multiply this by 2, now you get 1.5. So again there is the 1, keep a note of it. Again multiply by 2, just take this part and multiply by 2. 0.5 multiplied by 2 gives you 1.0. So you get a 1. That's it. Now you have a 1 over here, so you stop multiplying. So 0.875 in decimal is 0.111 in binary. These you have put not in reverse order but in usual order. So now 15.875 in decimal is 1111.111 in binary. Okay, frankly this was a coincidence. I didn't plan for all of them to be ones. Just happened to pick up numbers like that. So anyway, so here's how you convert from decimal to binary.